Hello. In this next video, the complexity of the Lewis structures that you'll be expected to know how to draw is growing, and this is the first video where we're going to look at Lewis structures for polyatomic ions. And we'll have to explain two new concepts, expanded octet and formal charge. The examples that I want to go over are shown here. And the example problem is draw Lewis structures for the following polyatomic ions. Before we get to some tips and the answers for these, why don't you name each of these polyatomic ions? Go ahead and test yourself. Go ahead and pause the video now. Okay. Well, let's go with this one first because we've learned all the 8s, nitrate, carbonate, sulfate, what else? Phosphate. This one is sulfate. S-U-L-F-A-T-E. When you remove one oxygen, you get the sulfite. And remember, you'll remove an oxygen, but you don't change the charge. NO3 is nitrate. OH is hydroxide. Okay, this may be something you might want to look up on the table. This one is another one that you may want to use a table, but really you should memorize it. You'll see this enough times in chemistry that you should know that this is cyanide. And this is from that mnemonic, Nick the camel ate a clam supper in Phoenix. Clam, this is chlorate. Okay. Now I highly recommend that before doing these types of problems or going through this video, you review the previous video 06OB50, which is the step-by-step drawing of Lewis structures, and you have practice with structures that are neutral, with compounds that are neutral. First, master this, and then you could go on to compounds that are charged, like the polyatomic ions. Remember, this video, the previous video, has the steps written out. There are 4 steps, and in this video, I went through these problems following these 4 steps right here. Okay. There's going to be some new concepts, though, when you're dealing with molecules that are charged, and also we're dealing with central atoms that have what's called an expanded octet. And let me take care of those 2 points first, and then we'll jump right into the examples. The first thing is there's a charge. Okay, so when you count the number of valence electrons, be sure to account for the charge. So, for instance, if I look at sulfite, SO3 2-, what I'm really showing is that there's 1 sulfur, which has 6 valence electrons, 3 oxygens, so I'll put here 3 times. Oxygen also has 6 valence electrons. But you also have to add 2 more electrons because it's a -2 charge, or a 2 negative charge. So this is plus 2. That added term is for the added electrons to make it a -2 charge, because -2. So instead of having 24 valence electrons, you have 26 valence electrons. Oops. Okay, so that's something new because we didn't have to add or subtract electrons when we were looking at neutral compounds. So that's the first new thing. The second new thing is formal charge, and I'll talk about it now. It will make a lot more sense when we look at some examples. So formal charge, let let me actually give one example now. For instance, if we have a carbon, okay, and I have, carbon to have 4 bonds, but that's if the carbon is neutral. If the carbon has 3 bonds and a lone pair, okay, this carbon has a charge. Just like these molecules have a charge, this molecule has a charge as well, and that charge is negative. Don't worry why it's negative just yet, okay? The thing is, I want my students to be able to put the charge next to the atom that's actually charged, not just think of the whole molecule as charged, which it is, but also that there's a specific atom in that molecule that has that charge or carries the majority of that charge. But let me give you an equation, and actually it's the equation that is on the cover page. Let me show you that real quick. It's formal charge minus, formal charge equals valence electrons minus, this is sticks plus balls. Sticks for every line, balls for every single electron. So a lone pair would be 2 balls. A double bond would be 2 bats. Okay? Valence minus sticks plus balls. Okay. Let me write that down so we have it at our disposal. Formal charge, Fc, equals valence, the number of valence electrons, minus, parentheses, sticks plus balls. Okay. Take it on faith that that carbon has 3 bonds in a lone pair, and that is a valid Lewis structure. Okay. You don't even have to take it on faith. Before we look at the formal charge, that carbon, does it follow the octet rule? Remember, when you count electrons for the octet rule, you count all the electrons around that atom. So you count both electrons of the bond. 1, 2, 3, 4, 5, 6, 7, 8. So it does follow, it does satisfy octet rule. That's interesting because just because it's charged doesn't mean it doesn't follow the octet rule. And actually, most atoms that are charged will still follow the octet rule. It doesn't follow the bonding rule that carbon has 4 bonds, but that's because that rule is for neutral carbon. This is an anionic carbon. If you want to use the formula, charge or formal charge equals the number of valence electrons minus sticks plus balls, you know that carbon brings 4 valence electrons to the bonding party. Minus, now we look at the carbon. It has 3 sticks plus, I know that we call this as one lone pair, but the pair has 2 electrons. So those are 2 baseballs. Did I do this right? Equals what? -1. Okay, negative. A -1. Put the negative near the atom that has the charge. So when we do the Lewis structures for these, I will require my students to put the charges next to the specific atom. For instance, this negative charge. Okay, I know I drew it next to nitrogen in the chemical formula, but in the structure, that you take that with a grain of salt because it could be on the nitrogen, it could be on the carbon. This negative charge could be on the hydrogen, it could be on the oxygen. We will have to figure that out when we draw the Lewis structure. Okay. All right, 2 things so far. We're counting valence electrons. The total valence electrons a little bit different because we have to add this twist because of the charge. If it's negative, you add electrons. If it's positive, you subtract electrons. Right? We won't get through this example most likely, but you know the positive polyatomic ion, ammonium. So here, I'll do it, the number of electrons. It's 5 plus 4 hydrogens, each has 1 valence electron. But now since we have positive, we minus an electron. So this is what? 9, this is 8. 8 valence electrons. Okay. 2 bullet points. Do I have a third? Oh, yes, I have a third. The third bullet point, we already talked a little bit about formal charge. The third bullet point is about this expanded octet. Okay, this is a kind of a weird one. We know that carbon, nitrogen, oxygen, when you fill up its valence shell, you have 8 electrons. Why do I say 8? Because in the 2 shell, you have 1, 2, 3, 4, 5, 6, 7, 8 electrons maximum in that shell. So we'll say it right now, carbon, nitrogen, oxygen, fluorine, they are going to want to try to satisfy the octet rule. 8 electrons around those atoms. But in the third shell, okay, so let me write this down. For C, N, O, F, okay, you do want to try your best to satisfy octet. And as a reminder, these are all in the second shell. Quantum number n equals 2. Okay? Or you could even think of it as second period. But look at the third shell, shell 3. We have the 3s, we have the 3p, but because the third shell has access to d orbitals, because you know that the first d row is 3d, n equals 3. It doesn't start at n equals 4. What that means is that elements that are in the third period have access to the 3d orbitals, and you could have what's called an expanded octet, or you don't have to follow the octet. You could have more than 8. So elements such as, so under carbon is silicon, then phosphorus, and sulfur. Chlorine, not so much, but yeah, I'll leave chlorine out for now. Okay, let me zoom in here. These, and they can have more than 8, and it's not specified. You'll just have to do trial and error. It doesn't have to be a certain number over 8. It doesn't have to be 10. It doesn't have to be 12. It can be. It just doesn't have to be. So these can have more than 8 electrons around it because, whoops, because n equals 3 has access to more orbitals, the 3d orbitals, right? Carbon, nitrogen, oxygen, and fluorine are in n equals 2, and they only have access to an s orbital and 3p orbitals for a total of 8 electrons to fill its valence shell. Okay. Those are the 3 bullet points that we'll have to consider because this is a little bit different than working with Lewis structures of neutral compounds and Lewis structures of compounds that have carbon, nitrogen, oxygen, and fluorine. We're going to see some expansion. It's kind of a weird name, expanded octet, because it's not even 8 anymore. It's more than 8 because we have sulfur. Okay, so here's sulfur right there. We'll see that it can have more than 8 electrons around it. Why don't we jump into that first example then? SO3 2 minus. SO3 2 minus. Essentially, we're following the same rules that we talked about in the previous video, how to draw Lewis structures, except we're going to add those 3 bullet points, and we're going to have to keep those in mind. All right. The first step is to count the number of valence electrons. Sulfur has 6, because I know that sulfur is right underneath oxygen. Oxygen has 6 also, but we have 3 of them. What do we do with this 2 minus? We add 2 electrons. So instead of having 24, we now have 26 valence electrons. Remember, with a Lewis structure, you have to show every valence electron as part of a line or part of a non-bonding electron. It could be a single electron or a lone pair. Okay, sulfur in the middle. That is the central atom. And I think the rule, I recall saying this in the previous video, if you're in doubt, the central atom is the one that's less electronegative, the one that's less likely to gain an electron. It follows actually the trend of electron affinity. Oxygen has a larger electron affinity than sulfur, therefore oxygen is more electronegative. The central atom is usually the less electronegative atom. The next step was to draw single bonds to all your outer atoms. Okay. So here's the trick, and it's actually a different trick than we discussed in the previous video. In the previous video, I asked you to recognize that oxygen brings in 6 valence electrons, and you would draw those 6 valence electrons, but one of them is part of the bond. And that's how you would figure out how many electrons goes on the outer atoms. But for these guys, here's a shortcut. Make the outer atoms satisfy Octet Rule. And remember, these atoms are the non-hydrogen atoms. Okay, let's try that. So for this oxygen to satisfy the Octet Rule, it needs 3 lone pairs, right? Because now we have 1, 2, 3, 4, 5, 6, 7, 8. So let's do that for all of them. Okay, so this is step 1. Step 2, if you need to add more electrons to reach what? To reach the valence count. Put those electrons on the central atom. Again, this is slightly different than what we learned with neutral compounds. For neutral compounds, I want you to understand how many electrons each atom brings to the bonding party, and then draw your electrons accordingly around this certain atom. Let's see if we have 26. 2, 4, 6, 8. So for every bond to oxygen, the bond and the oxygen, there's 8 electrons. So do you notice that if I have 3 of these situations, I only get up to 24 electrons. So I'm missing 2. Those 2 go on the central atom right here. Okay. Okie dokie. Double check that we have 26. So we have 2, 4, 6, 8. 8 plus 8 is 16. 16 plus another 8 is 24. And then 25, 26. Now here comes the kind of tricky part. There are, for some of these polyatomic ions, depending on the textbook or depending on the source that you check your answers with, there could be more than one answer. Okay, this is possible. We have the right number of valence electrons. Right now we're going to put the charge outside the brackets. So this is one way to show that it's a polyatomic ion. Okay, but I want people to show the formal charge. Understand what this means. This is your Lewis structure, and you have the whole thing is a net 2 negative. But I want us to use the valence electrons minus sticks plus balls to figure out the formal charge. And that's going to be important because this structure is not the most popular Lewis structure for SO3 2-. Okay. For this oxygen has 6 valence electrons minus 1 stick and 6 balls. So that equals what? -1. So all of these oxygens are -1 because they all have the same formal charge. 6 minus 1 stick, 6 balls. Okay. What about the sulfur? The sulfur has a valence of 6 minus. It has 3 sticks plus how many balls? 2 balls. And that equals 6 minus 5 is +1. And here we put a plus charge right there. Okay. This is actually one valid Lewis structure. So for my class, this would be valid. Okay. Valid Lewis structure. But in some textbooks and in some sources, they would rather minimize the number of atoms that have a charge and sacrifice the octet rule. But the thing is, sulfur can have an expanded octet. So this is another possible answer. Since sulfur can have expanded octet, you're going to try to minimize the number of charges. It's always going to be -2. Do you see how this is -2? Because it's 3 minus plus 1. So -3 plus 1 is -2. Okay. You notice that also I don't put the brackets in 2 minus because I am already showing the charge. Over here I'm not showing the charge. Okay. You should know how to interpret these types of structures with the brackets. But for my class, when I ask for the Lewis structure and there's a charge involved, I want students to put the charge where they belong, next to the atom that is charged. The thing is, there is a rule that if you can minimize the number of atoms that have a charge, do so, even if you disobey the octet rule. But again, phosphorus and silicon and sulfur can disobey the octet rule. That's perfectly fine. So what I'm saying here is that why don't we move one of these lone pairs? Because if I move, for instance, lone pair on the left, and everything else stays the same, look what we get. Here we have a lone pair. Is that better than this? Sulfur does not satisfy the octet rule, okay? But it's allowed to do that because it has an expanded octet. It has access to the 3D orbitals. So what's the advantage of this? The advantage of this is that there's only 2 charges, a negative here and a negative here. Take a look at the sulfur. Oh, let's take a look at this oxygen first. For the oxygen, it's 6 minus sticks plus balls, neutral. The sulfur looks weird, I know, to a lot of you because it doesn't satisfy the octet rule. Let's double check the charge though. Sulfur is 6 minus 4 sticks plus 2 balls. That's also neutral. This is also a valid Lewis structure. Some professors, including myself, would accept either. Okay, there are advantages to both, and in actuality, the real sulfite molecule is really a blending of these 2 Lewis structures. But for some professors, and it's not neither Well, there will be some debate. Some professor will say this is the preferred, and I'll put here preferred. It's because you minimize the number of atoms that are charged. Having a charge on an atom actually is a little bit destabilizing. It would rather be neutral. That will be a common theme later on in this unit. And here we have 2 atoms that are charged versus 4 atoms. If you want to follow that rule, perfectly fine. Just make sure that if you're going to try to minimize the charge and you're going to have an atom in the middle that's not an octet, that doesn't satisfy the octet rule, just make sure it's an atom that can have an expanded octet. Okay. Oh, man. So I know that was a lot, and that was just for the first one, sulfite. Let me do the next one, sulfate. Now that we've gotten a lot of these sort of subtle points across, let's see if it gets a little bit faster. So sulfate. How many valence electrons? 6 plus 4 oxygens that each have 6 valence electrons plus 2. 32, 34. Really double check because if you're trying to aim for the wrong number of valence electrons, it's going to drive you nuts when you draw the structure. 24, 30. Whoa. This is 32. That would have been bad. Okay, one more time. 24 plus 6 is 30 plus 2 is 32. Sulfur in the middle, 4 oxygens. Okay, yes, we already know that if all of these oxygens have the 3 lone pairs, so all of the oxygens satisfy the octet, okay, we would have charges on all those oxygens. But I'm not worried about that. I'm worried about, does my sulfur have any electrons? Well, 32 electrons. Each of this bond to oxygen has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 times 4 is 32. So there are no electrons, no non-bonding electrons for sulfur. But look at the charges. We already know from our previous example that when you have an oxygen with 1 bond and 3 lone pairs, they are negative. Okay. So I am jumping now to the formal charge. I'm not showing you the bracket version. Okay. The bracket version would be just go ahead and put square brackets and put a 2 minus outside of that structure. What is the formal charge of the sulfur? Can you do the valence electrons minus sticks plus balls? 6 valence electrons minus 4 sticks, 0, see, no non-bonding electrons, equals O. This is plus 2. That's not good. And this is a rule. This is not valid. No atom should be plus 2 or minus 2, plus 3 or minus 3. It could only be neutral, plus or minus. We have a plus 2, or you could say 2 plus. How do we solve that? We solve it by maybe neutralizing it. So I'm going to move these 2 electrons here. Do you know what that would do? We did it before. It would make that oxygen neutral. Not only would it make that oxygen neutral, it would actually make the sulfur plus 1. Okay, so I'm going to do something even more. I'm going to get rid of this charge, the one on this oxygen. Now it doesn't matter which lone pair on which oxygen you move. Okay, I just decided to move the lone pair on the left and on the right. Right now, I wouldn't have expected you to know that trick. What I do expect you to know right now is, can you draw, based on my purple directions, the new Lewis structure? The new Lewis structure tells me to put a double bond to these 2 oxygens. I will still have 2 lone pairs on each, right? Because I had 3 at the beginning, but when I move a lone pair to make a double bond, I'm left with 2. 2 oxygens on top, still the same. Okay. If this is true, all right, this is the preferred Lewis structure, preferred over this one, okay? But what do I have to verify? I have to verify that there are 32 electrons. 2, 4, 6, 8 on the left, another 8 on the right, so that's 16. And then 2, 4, 6, 8 on top, and 8 on the bottom. So that's 16 plus 16 is 32. That's a check. Are all the oxygens satisfy the octet rule? Because that was one of the rules. Make the outer atoms satisfy the octet rule. Okay. So all oxygens satisfy octet rule. That's a check. And you could double check here. This oxygen, 6 valence electrons minus sticks plus balls equals -1. So that's the formal charge. I was trying to figure out the octet rule. The octet rule is this: 1, 2, 3, 4, 5, 6, 7, 8. How about this oxygen here? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So all the oxygens satisfy the octet rule. The sulfur does not, but again, the sulfur can have an expanded octet. I just want to double check the charge. 6 minus, how many sticks do I have? 1, 2, 3, 4, 5, 6. How many balls, baseballs? 0. Ah, sulfur is neutral. Much better than having sulfur be 2 plus. This is the valid Lewis structure. Again, if you're just learning this for the first time, I know it's difficult. The thing is, you have a set of polyatomic ions that you need to memorize. The nitrates, the sulfates, and yes, the ites would be good to memorize also. Sulfite, nitrite, chlorate. Okay. So that is sulfate. All right, that's sulfate. And then when you make it an acid, H2SO4, it's naturally the 2 hydrogens are going to go here and here. But that's way in the future. All right, right now we have to figure out just the normal polyatomic ions. We have 4 more. I'm going to do nitrate, and then I'll probably assign this for extra credit. Okay, extra credit. But let me show you nitrate. Nitrate is, again, unusual. With chemistry, it's not a red flag that you don't know how to do something right away. It's a red flag when you've seen examples and you can't apply those examples to other molecules. It's a red flag if you see the same exact question and you can't reproduce the answer. Nitrate is a pretty popular polyatomic anion or a polyatomic ion. Let's do valence electrons. 5 plus 3 times 6 for the 3 oxygens. Oh, we have a negative charge, so we have to add 1. 18, 23, 24. Nitrogen is the central atom. It's less electronegative than oxygen. And we automatically put single bonds at first. And we automatically make the outer atoms fit the octet. So we have here how many electrons? 2, 4, 6, 8. And we have 3 of those situations, so it's 24. Ooh, we're done already. no electrons on the central atom. Okay. But what about the formal charges? This has a formal charge of minus. We've seen that already. Oxygen with 1 bond and 3 lone pairs. What about this nitrogen right here? Well, first of all, it has a charge of what? It has 5 minus 3 sticks plus 0 baseballs. That's plus 2. So this is oh no. But also, nitrogen is an atom that has to satisfy the octet rule. It violates octet. That's not good. So this is another oh no. Oh no, oh no. There are 2 things wrong with this. I would grade this as invalid. Wait a second. Oh yeah, it's still negative. Because if I put the 2 plus charge here, you see how it cancels out 2 of the negatives? So the charge is fine. The overall charge is fine. But again, you don't want any atom that has a plus 2 or plus 3, minus 2 or minus 3. You should only have plus 1, minus 1, or neutral. And N is an atom that has to satisfy the octet rule. It does not have any access to an expanded octet. So this is invalid. How do I make it valid? We got to keep all the electrons. So we know a way to get rid of this charge for oxygen by making a double bond here. What does that do? Let's stop right there and draw the result. Let's do the formal charge for nitrogen now. Oh, before we do that, we have these 2 lone pairs for oxygen, right? The formal charge for this nitrogen is 5 minus 4 sticks plus 0 baseballs. That's plus 1. Okay, it's still charged, but at least it's not a 2 plus. Okay, and see how it satisfies the octet rule? That's where we stop. We're done. N satisfies octet rule. Stop right there. This is your valid Lewis structure. Nitrate is a weird one because that negative charge that you see for NO3 minus is not due to only one atom being charged. It's due to having 2 oxygens negative in 1 charge and then central nitrogen positive. So overall that's negative. Okay? And then again, you will see in your textbook it drawn like this. But I want my students to be able to tell me what atoms are carrying that charge. Okay, we all know that the whole molecule in total has a net negative, but I want my students to draw this, okay, to show me where exactly those charges are, and to understand that it's not because only one atom is charged negative, it's that we have 2 negative charges and 1 positive charge. That positive charge exists mainly because we need to make that nitrogen satisfy the octet rule. That was the 3rd bullet point here. Okay, it's possible to get that nitrogen to follow the octet rule for nitrate. Okay. Like I said, let me leave these for practice or maybe extra credit, maybe even that one right there. So practice, practice, practice. But after you practice these 7, wait a day, wait 2 days, and see if you could reproduce these results. But also, you know that if you have nitrate, you should be able to draw nitrite. If you have chlorate, chlorite. Okay, what are we missing? We're missing phosphate, right? For the Nick the Camel, Ada Clam Supper in Phoenix. Phoenix stands for phosphate. Okay, good luck all. It just takes repetition and practice.